Yeah, thanks so much, Michael, for the very nice introduction. Also, thanks to you and Robert for the invitation. It's really, a great pleasure to be here and also to be back after 4 years. Now, I think we all know how tremendously successful AI is these days, but we also know that there are still certain problems concerning reliability. And in this talk, I would like to take you on a tour through where we stand today, what the problems are, what the chances are, but maybe where we also face challenges and actually limitations. I think right now we stand at the beginning of the fourth industrial revolution, and you see that AI already has a tremendous impact on our society. Think of self-driving cars, think of robotics, think of telecommunication, and then also even more sensitive areas, like, for instance, the whole legal system. So in the US, for instance, decisions are already, not completely decided by AI, but prepared, and also, for instance, the job sector. And then certainly the whole area of sciences. I think there is not one discipline which does not use AI these days, ranging from medicine or biology up to even humanities. And I think everything we know got a huge push right now with these huge foundation models, ChatGPT, which have their own challenges and advantages. And I think it's fair to say that we will see a radical change of our society in its full breadth over the next years. On the other hand, there are also warning voices. And so there was an interesting incident. It's now already 5 years ago at one of the big AI conferences where one researcher, Ali Rahimi, gave a plenary speech, and he said, machine learning, so AI, is still at the level of alchemy. And his argument was that researchers do not know why some algorithms work and others don't, nor do they have rigorous criteria for choosing one AI architecture over another. So now we have worked hard. We are 5 years further, and certainly we made huge progress. But if you think about, if you train a neural network, it's still a lot of trial and error, so there are still a lot of theoretical foundations missing. And then there are also even more warning signs. So for instance, Stephen Hawking said the development of full AI could spell the end of the human race. I think one can have different opinions about that. There is certainly a danger. And if you look closely, in fact, there are already still many problems with reliability. So think, for instance, of problems with safety. There were already various accidents involving robots, and after all, a self-driving car is nothing else than a robot. Also problems with security. One can hack into these systems, maybe modifying data slightly so that a human would not observe it, but the decision will change radically. In particular, dangerous, for instance, for hospitals. Problems with privacy. These methods are extremely data hungry, and so in particular, in the health sector, it's a huge problem to gather enough data, and therefore privacy violations happen worldwide on a daily basis in this respect. And also problems with responsibility. A lot of these decisions are black box decisions, and also often decisions are biased. So in that sense, I think it's fair to say that one major problem these days is the lack of reliability of AI technology. But in fact, we see also a lot of positive signs. So for instance, also politics is working in that direction, and I'm sure you're aware of the fact, now in the EU, we have the AI Act of the European Union, and also worldwide, the G7, they met last year in Japan in May, and so there they started the Hiroshima AI process, also to pose international regulations on the usage of AI. Now, to ensure reliability really in its depth, from my viewpoint, what is absolutely essential is to get a deep theoretical understanding of it. And only then we can know that, in fact, we have absolute security, safety, and so on, and all these aspects. And so my talk will be now from a mathematical, theoretical perspective. Don't worry, it will not be too mathematical, so I will keep it on a high level, but I would like to show you a bit this viewpoint from this direction. Okay, so AI is a huge area. I don't want to cover, I cannot cover everything, so I will focus on deep neural networks, which are, as we all know, also the workhorse today of artificial intelligence. And they are not new. In fact, everything started a long time ago, as you probably also know, in 1943 with McCulloch and Pitts, who wanted to mimic the human brain and introduce artificial intelligence that way. And so what they did was they developed a mathematical model for a neuron and then put this together to obtain a formula for a neural network. So this is an artificial neuron. We have these input, x1 to xn, then we have the weights and the bias, and we have the activation function. And so the weights and the biases, as we know, this is what is learned in the learning process. And if you put everything together, you get a formula, a mathematical formula for what a neural network is. It's a highly structured function, which is composed of these terms, these affine linear terms and activation functions, typically the ReLU. And so these affine linear functions are then learned in the training process. So what are the key theoretical directions we need to ask to understand what happens now in deep neural networks, how they act? One first direction is expressivity. Yes, think of if you use a neural network, the first you need to decide is how many layers to take, how many neurons in each layer, how to set up the architecture. So this is the area of expressivity, asking how do we set up the architecture the best way to approximate the functions I want to learn. So this is from a mathematical viewpoint, approximation theory, applied harmonic analysis, and maybe the most evolved theoretical area these days. Then we train the neural network. So this is the second question we need to ask. How does the training algorithm perform? We usually use stochastic gradient descent, and then we optimize over a very ragged landscape, aiming to find local minima, which are good for generalization. Still a mystery why this works so well, because the problem is highly non-convex. And also there are a lot of mathematical theories are thrown onto, also exotic ones like algebraic differential geometry, which aim to understand the shape of these local minima. Then generalization. So now we aim to test our neural network, how good we did. We test it on test data and hope that it generalizes well. And so this is sometimes also called the Holy Grail, because what we want in the end are success guarantees. And in fact, many areas or some areas like electron tomography don't use these methods right now because they don't have a ground truth. They see everything through the algorithm, so they have to trust the algorithm completely, and without error bounds, this is just not possible. And then there's another area which I also find extremely important, which is explainability. So now we have to train neural network. We are asking, how does it perform? Why does it reach certain decisions? What are the key features of the input to reach a certain decision in the end? And so if you look in the EU AI Act, you see that there's also the right to explain. So every AI technology has to have explainability associated with it. And in my talk, I would like to focus now on these 2 points. As I said, generalization being maybe the holy grail of artificial intelligence, and explainability also being extremely important for trustworthiness and also for legal reasons. And for generalization, I would like to show you one result which solves this problem completely in a specific problem setting. And there I would like to take you now in the area of graph neural networks, which are generalization of normal neural networks, because you can also view Euclidean data as a graph. So graph neural network acts on graph signals, and the graph signal is you have the graph nodes, and for each graph node you have a feature vector. So this is a traditional setting, and this is where graph neural network acts on, and they are extremely popular. There are thousands of applications, so recommender systems, fake news detection, so social networks, but also areas like, for instance, chemistry, because a molecule is nothing else than a graph. And so in this area, we can now ask a very specific generalization question. Maybe I should first say, so we now use convolutional neural networks, so graph convolutional neural networks. And convolution you can define in different ways, as you might know. So you can define a convolution in the spatial domain, where you have a filter matrix in which you move on your graph. Or you can define convolutions in the Fourier domain, in the spectral domain, where you use the convolution theorem, and then you have also a bit more mathematics involved. And so here in this talk, we will focus on the second part, and I will say in the last slide, basically also that you can do something similar for the spatial approach. And then the activation function, that's just similar, you apply it to every node. And the pooling layer is also not that difficult to generalize to graphs, because you just fuse basically certain nodes and then get your coarsening graph. Okay, so generalization question is, as usual, we have graphs. Maybe we have, let's say, the graph on the right-hand side in our training data set. We trained our graph neural network, and then we are asking, does it generalize also to this graph on the left-hand side? But here we can ask, let's say, a bit more specific question, because as you see, these graphs kind of look alike. And if 2 graphs, I should say vaguely, model the same phenomena, then certainly we expect that our graph convolutional neural network has the same repercussion on both, approximately the same. What it means, model the same phenomena, we need to make precise. But this gives you already a visual impression. And so what I would like to show you now, the first part of the talk is that we can completely analyze this subproblem and get precise error bounds for the generalization ability. If we look at these graphs, we have one in the training data set, and then we have one which looks kind of alike in the test data set. Okay, so first we need to define what we actually mean by convolution. So this is a bit delicate issue. There is a very canonical way to define convolution for graph neural networks. So here you see the graph Laplacian. So you have a graph, you have a degree matrix, an adjacency matrix, that's the graph Laplacian, and you can also normalize it. So what does it do? Well, a graph Laplacian is, you can view it as an operator, it's half-adjoint, so you have eigenvalues, you have eigenvectors, and it encapsulates the geometry of the graph, and you see this here, so you see here some of the eigenvectors, and basically you see here the different frequencies adapted to the structure of the graph. Okay, so that's the graph Laplacian, and then, using the eigenvectors, you normally define the convolution operator in the following way, as you see here. So you have here your input graph, you have here the eigenvectors, and then this here is your filter. It's a discrete filter for the convolution, and this way you define convolution. That's the standard way. But there are a lot of problems. First of all, it's computationally extremely demanding. So, computing the eigendecomposition in large friendship graphs, it's basically impossible to do that. Also, you don't have an FFT for graphs. That makes computing this inner product very challenging. But worse comes to worse, this will not be transferable, because if you have a graph and you perturb it slightly, then certainly you would like that these remain in the same class and model the same phenomena. But the repercussion will be very different, because if you perturb the graph slightly, these eigenvectors will change a lot, and so the convolution will change a lot. There's no way, if you use this convolution, that this becomes stable. So we need to put a bit more thought into that, and there is a way to cope with this problem, and that's like sometimes in mathematics you have this phenomena that here you have a discrete object, and if you make it continuous, things become much easier. And we will see this phenomena later on also in the talk again. And so there is something which is called functional calculus. It's a beautiful theory from mathematics. I don't want to involve you too much into that, but so what it basically does is, if we have here, for instance, think of this as this graph Laplacian. And so we have this very nice formula for graph Laplacian. Then there's a method in mathematics where you can say what it means to apply a function to it. So for instance, g could be the square function, t squared. So this function is now a continuous object, and you have a way to define what this actually means. And so the decomposition looks like this. So this g is then just put on the eigenvalues. And this you can also write down in many cases explicitly. If it's a rational function, you have a term for that. So if g is, for instance, the square function, it is just t squared. Or if it's, as he says here, a rational function, then this g of t, you can write it down explicitly and compute it directly. Okay, just keep that in mind. So now, what we do is we basically replace this discrete filter for the convolution by a continuous object, namely this function g. So what we do is now we define the convolution in this way. So now you see, what we had before is basically now replaced by this continuous g. So the convolution, so the g is now basically the filter, and the convolution is apply this filter to your graph Laplacian, where the graph Laplacian encapsulates the geometry, and then this is now the convolution definition, instead of what we have here. So the main difference is now, if you look at the right-hand side, that instead of here having these fixed filter coefficients, we have now this object. And this makes a huge difference. Why? Well, first of all, it solves the instability problem. Because now if I change my graph slightly, and the eigenvectors change a lot, then this will counterbalance it, because here the eigenvalues are contained in it. Here this has no chance, it's just fixed. So this gives the stability for this object. And then it also solves the computational problem, because now if this is a rational function, you can write that down explicitly. You don't even need to compute the eigendecomposition. Okay, so this is now how we'll define convolutions. So how do we define stability? Or let's say that two graphs model the same phenomena. So there are a lot of ways to do that. You see 3 here. So first of all, you can say, I have a graph, I perturb it slightly. 2 graphs which are small perturbations of each other, these are in the same class. Or you can say you have some continuous object, and if 2 graphs are sampling from the same continuous object, then these are in the same class. Or there's also a graphone approach, which says there's like a continuous graph, and you have a sequence of discrete graphs converging to it, and if my 2 graphs come from this sequence, they are in the same class. So we will go with the second approach. And so how does the second approach look like? You have your graph, which are points, nodes, and the connections are weighted. You have this continuous object which lies on top, which consists of points and distances between the points. And so the correspondence is, now you sample this continuous object, and so if the distance is small, then you will put a weight on it, which is large. And so basically, in a nutshell, graphs that represent the same phenomena are discretizations from the same continuous space. Okay, so far so good. So now everything is in this picture, how things work and how we can set it up. So let's assume one of these graphs is in the training data set, the other's in the test data set. So what do we do to analyze it? We have our continuous space, which is now the same for both. And let's say we have a function on that. And we want to compare the repercussion on both of those. Okay, so first of all, we bring things down to the graph. So we sample it. That looks like this. So we have the sampling of both of these same continuous functions. Then we need to apply the filters to it. So the convolution. Remember, the convolution is this function, this continuous function g, applied to these graph Laplacians, but they are different for both graphs. So we apply now the convolution, which is the same function g with these two different graph Laplacians. Okay, so the filter or the convolution is now applied in an adapted manner depending on the graph. Okay, so now we need to bring everything back to the continuous space because that's what's similar, and that's where we can compare things between both graphs. So we bring things back up, and then we can look at the distance. So you see here the power of having a continuous object, that there you have, let's say, a common layer where you can compare things in a very correct manner. So you have these objects to bring things on both sides down. Okay. So this is basically how things work and how you set up the proof and the results. And let me just say, this way you can show that the error which you make by transferability of a graph convolutional network, if you have, let's say, one graph and you compare it to the continuous setting, you have precise estimates by the transferability of the graph Laplacian and the consistency error, which is basically the sampling error if you sample things down, so how dense this graph is in your continuous space. And then, the full result, as I said, it's very technical. I don't want to bother you too much with the details. Looks like this. So you have these 2 graphs, which are your input graphs. You have the 2 graph Laplacians. You have your convolutional neural network with so-called Lipschitz filters. You have the graphs. If you move your graph through the different neural networks, neural network 1 and 2. You have certain error bounds which you need to satisfy, and then here, this is the full error, and you see you have a very precise error bound for that, where certain aspects come into play. You have the number of layers here, you have this delta here, d is a constant of these Lipschitz filters, and then you have here, the so-called Pauli-Wiener space involved, the dimension of that, and that also appears. So, just in a nutshell, for this, a bit more special situation of generalization for graph convolutional networks, you now have a very precise error bound, how you perform then on test data, if the test data is in the same class, let's say, as your original training data. Okay, and so this is one example, and you can extend it to different settings. So you can extend it to this graphone setting, where now you define being in the same class as being in the same sequence towards a continuous graph. And also we lately also transferred it to message parsing graph neural networks, which is now this spatial domain convolution, and so also there you get nice generalization points. Okay, and what you see here is now, some experimental data. So this Cayley graph is based on spectral filters, and this is based on this is based on spatial filters, and you see, so here, you have an image, and basically these images are in the same class, they are just different resolutions. And you see, that the accuracy also experimentally from this Cayley graph is much better than from the other graph. So this compares, let's say, the spectral domain or spectral graph convolutional neural networks with spatial ones. And concerning the error bounds which you have, this linear behavior, you also see experimentally. So here you have, for instance, you have graphs with different perturbations, and this Laplacian error behaves linearly with respect to the filter error. So this kind of confirms that what we see theoretically can be also witnessed experimentally, and it's a correct, let's say, mimicking and explanation for that. Okay, so this was, let's say, a short introduction to generalization, and there are a ton of results. We were very excited to work in that direction because, as I said, it's kind of the holy grail, and also people aim to explain, for instance, this double descent phenomena and so on, which you observe. So now let's delve also a little bit into explainability. So explainability is, I think, also a very exciting area. It's on a bit more vague feet, let's say, than generalization, because there's no precise definition of what an optimal explainability approach is, because it's highly interdisciplinary what an explanation is anyhow. Okay, so but the main goal, you've seen, I guess, pictures like this. So you have a 3 as an input. The neural network says, this is a 3. And then the explanation is a heat map, which indicates that these red pixels are very important for the network to reach that decision. And maybe the blue play against it. And that makes a lot of sense because these openings distinguish a 3 from an 8. So looking at those makes a lot of sense and is very meaningful. But then, from a mathematical viewpoint, I have to say, so this is typically called a relevance map. So what is relevance? What does it actually really mean? We always aim for optimality. What is an optimal relevance map? Also, what about other modalities than imaging modalities? And also, why should a pixel be important or not? Shouldn't it not be combinations of pixels? For instance, if you look at a lake, then maybe the waves, the form of the waves are important, but not every single pixel. And ultimately, what we aim for in that area is to be able to question an AI like you would do your colleague about a decision. And so with ChatGPT, we are one huge step further. So we also work in this direction now. But this is in the end what we aim for, to communicate with AI like you do with a human. But there's one thing I would like to point out, which I think is sometimes forgotten in this area. If you want to use an explainability approach to ensure reliability, then this approach better be reliable itself. Yeah, it's nice to produce these very nice pictures which look like heat maps, but you need also kind of theoretical foundations for the explainability approach, because you need to trust it to be able to say, indeed, this is why the decision was taken. So let me walk you through one of the approach we introduced, but there are also a lot of others certainly, which is based on information theory, rate distortion theory. So information theory is a very exciting area. One main goal of it is the following. So you have two persons. One has a message, and she transmits parts of the message to Bob at a certain rate. Then Bob has to decode it, and he will make an error. That is the distortion. Yeah? So you want to transmit a message at a small rate, but also the error, the distortion, should be small. Yeah? So this is, let's say, rate distortion theory in a nutshell. And now we can transfer this explainability question into this framework. So Alice has the original image, and she has the neural network. And Bob has also the neural network. Now Alice is allowed to transmit parts of the image to Bob, hopefully the relevant parts. And so then Bob has a bit of a problem, because now he has this partial image, and he has to bring it back to the image size. He can do that maybe by obfuscating with random pixels, and then he puts it in, and he will make an error. So you have here the rate, how many pixels are transmitted, and we aim for conciseness, to have very few relevant pixels. At the same time, the distortion should be small, namely the difference between these outcomes. And so this leads to the following problem. You would like to have very few relevant pixels, but also the error should be small. And if you work in optimization theory, you will immediately say it is impossible to compute. Yeah, I mean, you can prove all these nice complexity results, it's NPPP complete, and so on and so on. And if you have some problems of that type, you relax. And so instead, I mean, what one can then compute, a relaxation, is this optimization problem where now we optimize here again over the distortion. And here now we don't have a 1-0 decision, relevant or not, but we have, again, a relevant score between 0 and 1, and the L1 norm promotes sparsity. And the lambda balances between how much you will put emphasis on a concise explanation versus how much emphasis you put on having the error small. And because this is now a concrete optimization problem, you can also have a rigorous mathematical performance analysis. We can extend this also in two ways. First of all, you can say, well, this obfuscation with random pixels looks very strange. Why don't you use an in-painting gun? So we can do that. And also, as I said, why should every pixel be important? And in imaging sciences, if you work in that area, there are beautiful representation systems, so you can represent your image in very meaningful ways. One very popular, which is the basis also for the JPEG 2000 standard, is a wavelet decomposition. Wavelets look like this, and you can write every image as a linear combination of these wavelets. And so then you can put relevant scores on the coefficients of these wavelets. And this is what we then call cartoon X. And this also has a very nice relation to image compression. So image compression is the following. You have an input image, you compute the wavelet decomposition. Then, it's a bit dark, but I mean, I hope you see it a bit. So then you select the largest entries, you put everything else to 0, and you only store those which are not equal to 0, which gives you the high compression rates. Then from these coefficients, you want to reconstruct your image, and hopefully it is close to your original image. So that's image compression in a nutshell. And now with cartoon X, it is in the same spirit. You have your input image, you compute, let's say, a wavelet decomposition, you select the largest entries, you replace the others now with random noise. Certainly, if you reconstruct from that, you don't have any chance that this is close to your original image, but this is also not what you want. What you want is, through the lens of a neural network, this should be close. So if you look through the neural network, which gives you the distortion, then these two images should be close. Okay, so let me show you two examples, what you can do with that. So this comes from telecommunication. What you see here is a city map. You have here these red dots are cell phone users. The white blob is a cell tower. And the network computed this, so it's a double unit, computed this black and white background, which indicates at each point how strong the signal there is. And now you see something strange happening. So you see this dark area here. So the network says if you stand here, you have a really bad reception, which cannot be because you stand right in front of the cell tower. And so you can now ask this explainability approach, why did the network reach that decision? And so the explanation is on the right-hand side. So the network looked at these buildings and these cell phone users. And in fact, they actually have bad reception. And so what turned out later on was there was actually a building missing in the city map. So the network did something meaningful, but the data was faulty. And so this you can find out via these explainability approaches, for instance. And then there are also, let's say, a bit more cute examples, for instance. So here the network really reached a wrong decision. So it said, this is a diaper, although it's obviously a man with a dog. And it said, this is a screw, although it's also obviously a man with a sweater. And so now with this, let's say, higher level explanations, so not pixel-based, but higher level explanations, you can put on top what the network actually has seen. So I will put it on top. And then you will see what the network has seen to reach this wrong conclusion. And so if you look at these pictures, you see this looks a bit like a baby. So a diaper is not that far off, and this looks a bit like a screw. And so then you see what the network has maybe mistakenly interpreted, and can correct for that afterwards. And so we have now extensions also using not wavelets but shearlets, which are a bit more even sophisticated representation system, which also allows information about edges. Okay, so this was, let's say, a bit of a tour in generalization and explainability from a mathematical viewpoint. And in the last maybe few minutes, I would like to also touch upon one point which I think is often neglected, but I think it's extremely important, which is asking about limitations. Are there actually fundamental limitations to these methodologies? And so we looked a bit into that, and there are different ways from which you can interpret this question. So what we looked at is what can you actually compute on digital hardware. So you train your neural network on certain types of hardware, and the question is, which impact does the hardware have on your results? So first said, artificial intelligence is not a Swiss Army knife. I think this is something which maybe also in industry everybody should remember. It's not, let's say, a universal tool which, let's say, works for everything. And we looked at it from a computability viewpoint. What can you actually compute on digital hardware? Because, I mean, many of you have a laptop in front of you. This is all digital hardware. And you break everything down to zeros and ones, although the problem is continuous, often of a nature, and this has to have certain restrictions. And there's a beautiful model for digital hardware, which is the Turing machine, and it's widely accepted that basically everything you can compute on a Turing machine, you can compute on digital hardware, vice versa. And so, in a nutshell, a computable problem, so there's this computability theory in computer science, is one for which the input-output relation can be computed on a digital machine for basically any given accuracy. If something is not computable, well, I mean, certainly you can put it in your laptop, you will get a result out, but then you have a problem with accuracy and also with theoretical guarantees. Okay, so what we found out is that in fact, I mean, for instance, if you look at so-called inverse problems, which are often used in medical imaging, the solution of a finite-dimensional inverse problems is in general not Turing computable by a deep neural network. So this is certainly a bit disappointing because, I mean, today you perform computations almost exclusively on digital hardware. And so, let's say what it causes are many problems. I mean, first of all, you don't find, let's say, general algorithm which gives you any given accuracy. In that sense, you don't have reliability of the output, and also it could point why we see these instabilities and non-robustness in general. So this is a bit disappointing, and also you cannot say this problem is computable and this not. And also it has nothing to do with the condition number, because you could imagine the condition number, then also it's not computable. I mean, there's also no relation there. So sometimes you have a consistency bad error. But on the other hand, I mean, there are good news. Also theory tells you that if you go now from the digital world to the analog world, and there's a beautiful model, it's the so-called Bloom-Schupf-Smale machine, then suddenly things become computable. Yeah, so that means that maybe reliability for certain problem setting might require novel hardware types. And there are exciting developments in that direction. So, for instance, neuromorphic computing. We already have neuromorphic chips and could use that. Biocomputing, which is in a preliminary stage, but also this is on its way, and then quantum computing certainly as well. I mean, many universities worldwide have quantum computing centers, and also industry goes in that direction. And so this computability issue, I mean, we have many results in this direction. Classification problems, the pseudo-inverse, also in the PDE world, sometimes things cause a complexity blow up so that the complexity, the output of the complexity is exponentially higher than from the input, and so on and so on. Yeah, but I think the future perspective from my viewpoint should be, I mean, first of all, we would like to design our hardware, maybe augment digital hardware by analog hardware so that we have provable computability, that we also have performance guarantees, so from the generalization viewpoint, that we fulfill the legal requirements, which is, for instance, algorithmic transparency, accountability, and also the right to explain, because you can show that in certain instances, also algorithmic transparency might be a problem for digital hardware. And finally, what I didn't touch upon, but what I think is extremely important, is the energy question. I think we all know how much energy is consumed by these GPU centers. And this, I mean, here I just brought you a picture. So this is from the decadal plan of the Semiconductor Research Corporation. in the US. And so here you see the world energy production, and you see only for communication, so only the energy we need for communication will reach in, well, I mean, maybe 10, 15 years, the size of the world energy production. So then, I mean, we cannot heat our houses and so on and so on. I mean, we maybe can communicate, but nothing else. And even that causes a problem. So that is a much more serious problem than I think is maybe worldwide known. And also, I mean, going in this direction of analog hardware could, to a certain extent, cope with that. So, so let's say the goal would be truly reliable AI by next generation computing. Okay, so let me come to a conclusion. So from my viewpoint, we live in, concerning research, really exciting times. I mean, artificial intelligence is, an amazing, let's say, method and technology. We see impressive performances, but we also have this major problem with reliability. And so I took you on a tour from a mathematical viewpoint. I showed you mathematical directions, expressivity, optimization learning, generalization, explainability. We delved a little bit more into generalization and explainability. And also, we touched upon that there are, from a computability viewpoint and also from limitations, one main problem which you could solve maybe by next generation computing. And so as already, Michael said, let me add one more slide because we talked a lot about reliability. And so in Munich, we just set up what's called a Konrad Zuse School of Excellence in Reliable AI. It's set up between both universities in Munich, so the TU Munich and the LMU. And you see here the research focus. Mathematical algorithmic foundations is one main research focus, and the others are medicine, healthcare, robotics, interacting systems, algorithmic decision making. Everything is intertwined with reliability aspects. So the education is a structured master program, plus a structured PhD program, so you can enter both at any time. And we also have a call right now out for PhD positions. So if you know someone or someone is interested, you can also contact me. All the information is also on the webpage. And with this, I'd like to conclude and thank you very much for your attention.